I'll first introduce Mr. Ravinder Kumar, Deputy Group Manager, Technical Services, Axens India, for his first presentation. He has joined Axens in 2009. Previously, he has worked with RCF and Indian Oil Corporation. Right now, he is working on various technologies. He is a graduate from Indian Institute of Technology. Over to you, Mr. Ravinder Kumar.
Good afternoon, everyone. So let's have something of, about the technical. We all in refining and petrochemical industry strive to improve the process so that we can increase our gross profit margin and the challenges while ensuring the harmony with the environment. So today I am going to present Axens' endeavor to achieve the same objectives from reforming Symphony catalyst. So I will start with the introduction, then little bit about the reforming catalyst function, what are the axes of catalyst development, superior catalyst carrier, and superior metal interaction, reforming catalyst portfolio, and in last, Symphony for CCR application. So what is our expectation with the reforming catalyst? What is the market looking for? First, no doubt, the better C5+ hydrogen aromatic yields with the initial catalyst performances. Second, better economic throughout the catalyst life cycle with the high activity and the yields stability. Third, high on-stream factor with no DP issue, no fouling and no corrosion with the improved catalyst particle strength and the better chloride retention. So Axens reforming Symphony catalyst very well fulfill these demands. This is what we are going to show in the next slides. Symphony catalyst was officially launched in 2013. So catalyst structure. We all know catalyst structure. The catalyst particles are aggregates of alumina crystallites with the macropores and mesopores. Macropores are like inter-aggregate highways, whereas the mesopores are intercrystallite streets that provide space and a passage for the reactants and products. And reforming catalyst is a dual functional with acid and a metal functionality. Acid function is by hydroxylated gamma alumina support material, and we know that we have to maintain around 1% of the chloride on the catalyst to increase the acidity and to stabilize the platinum dispersion. Acidic sites catalyzes isomerization, cyclization, which are the desired reactions, and hydrocracking reactions, which are less desired. And the platinum metal sites catalyzes dehydrogenation, which is a desired reaction, and then the hydrogenolysis reactions, which are not that much desired. So additional elements are added to enhance the performances. Example, tin in the CCR catalyst. So tin, which interacts with the platinum for the better yields and less coke generation. Tin also interacts with the alumina surface to improve yields by reducing cracking and to increase the catalyst stability. Therefore, acid and metal function must be balanced for the best performances. Okay, before coming to the axis of development, let's try to understand the surface area loss with a golf ball analogy. Surface area for a new golf ball is around 71.6 centimeters square for 2.05 centimeter of radius and 150 dimples of 0.2 centimeter. Whereas for equal solid volumes pair, the surface area is 50.3 centimeters square. So here what I am trying to say is there is a loss of around 30%. Now the hydrothermal stability decreases with the water and the temperature. We know that reforming reactions are endothermic in nature. So the average temperature in the reaction section is lower than 500 degrees Celsius. But we need to regenerate the catalyst. We have to burn the coke in the regeneration section. And the temperature is comparatively high in the range of 540 to 580 degrees Celsius, depending on the coke content. So, and high moisture is also there. So here is the surface area stability with the temperature. We can see with each step increase of 50 degrees Celsius, there is a loss of surface area. Similarly, here we can see with the increase in the moisture in the catalyst, there is a decrease in the surface area. So high moisture also reduces the phase change. As we know, the gamma alumina phase is the active. And at very high temperature, this phase, gamma phase, can change to the alpha phase, which is in inactive state. So at the high moisture content, this phase temperature will also reduce. Okay, what is the impact of surface area loss? So loss in the chloride retention, resulting in higher chloride injection rate, higher chloride content in the gas phase. That could lead to the corrosion, short duration of chloride traps, problem of green oil, and increased downtime of compressors, that is high maintenance work. It also leads to loss of platinum dispersion, less active sites, increased coke impact at a lower coke percent, fast deactivation, shorter catalyst lifetime, more regeneration in CCR is required. So therefore, based on that, the first axis of development is the superior catalyst carrier, which is alumina. Alumina support properties depends on the source of raw material, manufacturing process control, crystallite size, pore size distribution, transition alumina phase, control of the crust strength, and the surface area. Additional elements are added to enhance the yields and the stability of the catalyst. And the second axis of development is the superior metal interaction. Reactions like dehydrocyclization and hydrogenolysis reactions require adjoining platinum atoms. Here you can see in a 13-atom platinum cluster, 12 atoms which are adjoining and available to catalyze the reactions. Moreover, very few, around 4 to 5 large clusters can exist on a single crystallite. That ensures good platinum dispersion and better metal interaction. So our long track innovation leads us to the Symphony catalyst family with both optimized metal and acidic functions. So we have worked a lot on enhancing our supports in terms of the surface area stability, which is the key to ensure the maximum chloride retention, specific surface area to disperse the platinum, which reduces the chloride injection and minimizes related issues. So our supports are characterized by their high alumina phase purity, and this contributes to the improved catalyst properties such as long and higher yields. So innovation of the metal functions improves the yields and the platinum dispersion retention. So Symphony's catalyst series offers optimized catalyst properties and outstanding robustness thanks to the Axens' latest innovation on both metal and acid function. Now the Axens reforming catalyst portfolio. So we have wide reforming catalyst portfolio that fits any kind of technology. All catalysts are designed to ensure the maximum profitability. So for the fixed bed reforming catalysts, these are the Symphony series catalysts P152 and PR150, PR156, and the new catalysts which were introduced are P252, PR250, and PR256. So here are the results of the third-party pilot test. Comparison of the new PR256 with the old RG series catalyst indicate superior selectivity and the improved activity of the PR256. Activity of the PR256 is high by 5 degrees Celsius, and the yields are better by around 0.58% at the beginning itself, and around 2.8% at the later stage. Stability is improved by around 37% at the longer catalyst life. So these are the pilot test results of IFPN for the new generation 250 series. So here is the comparison of PR156 and the new PR256 that indicates a better activity by around 4 degrees Celsius and higher stability by around 12%. So as on date, we have number of references for Symphony fixed bed fixed bed catalysts are more than 120 by customers and more than 150 by catalysts. So PS100 is a Symphony catalyst, and the new Symphony catalysts introduced are highly active CR157, AR151, and PS110. So PS100 and 110 are low density catalysts for competitor units. So we have over 50 references as of now till March 2022. All types of design, repeated orders from the majors in units loading Axens catalysts for the first time. So we have been just awarded in the Asian region with the CR157. Now the application of the Symphony catalyst for CCR units. The PS Symphony stability. So high hydrothermal stability is the key parameter for catalyst performances on the long run. Same surface area decline range for the Symphony PS40, PS100, and PS110 has been observed. CR157 also offers same high hydrothermal stability like PS100 and PS110. So Axens catalyst outstanding hydrothermal stability is demonstrated in both Axens and non-Axens design units. So here is the comparison of the PS100 with the new Symphony PS110. PS110 is more active by 5 degrees Celsius and high C5 plus and hydrogen and aromatic yields. Here we can see the C5 plus and aromatic yields are around 0.8% higher, which definitely boosts the reforming unit margins. So here is the activity performance feedback of PS110 from the competitor design unit. So here we can see the normalized weight is in line with the projection estimate with only plus minus 5 degree Fahrenheit of variation. Normalized weight accounts for all variation in the daily operations. And the selectivity performance feedback of the PS110. Here we can see the normalized C5 plus yield are doing better than the projection estimate with only 0 to 1 volume % of variation. And Symphony CR157 and AR151. So CR157 for the gasoline mode was launched in 2016 and AR151 for aromatic mode was launched in 2017. So like all other Symphony products, these are also offering the best hydrothermal stability and to maintain the best performances on long run. Symphony CR157, based on the actual data, CR157 is 5 degrees Celsius more active with around 15% of high stability compared to CR607. And same CR157 selectivity is same as CR607. So I would like to share a few references for the CR157 catalyst activity and selectivity. In the first reference, that is for the competitor design unit, here we can see the delta performance, actual delta performance, and with the guarantee parameters is varying from 0.6 to 2.3%. So average is around plus 1.2%. And the second reference we have, that is also from the competitor unit. So we have received the recommendation letter from the customer. So I would like to read the letter. The objective of this unit is to produce high liquid yield reformant with a high octane number around 102 minimum at the stabilizer column bottom. The unit includes the following section: reaction section, stabilization section, atmospheric catalyst regeneration section. Unit until April 2017 year, the catalyst supplier of this unit was another competitive catalyst company. And the unit 440 has been loaded with the CR157 Axens catalyst in first quarter of 2017 and smoothly commissioned with the support of the Axens on-site representative. Ever since, the unit has been operated satisfactorily and produced desired product specification and did not require any specific unit parameter adjustment with the Axens CR157 catalyst. Third reference is comparison with the former generation catalyst regarding the activity. So CR157 was loaded, and after here we can see after loading the CR157, the weight requirement is 505 degrees Celsius compared to the last catalyst weight of 512 degrees Celsius to achieve the same RON. And regarding the selectivity, the C5 plus and hydrogen yields were similar to the last catalyst. Therefore, same selectivity with the improved activity. And the fourth case study is again a comparison with the former generation, the activity. Here we can see the CR157 catalyst is more active by 5 to 7 degrees Celsius compared to earlier CR601. And yes, again, the performances are confirmed, same selectivity with an improved activity. Fifth case study. So this is in the competitor CCR unit. Here, all the performances are above the guarantees. We can see all hydrogen yield, C5 plus yield, aromatic yield, RON, all were higher than the guarantee parameters, and that were at lower weight of 522 degrees Celsius compared to the guarantees, which the estimation was at 528 degrees Celsius. Sixth case study. This is again in the competitor design unit. Here, after replacement of the catalyst with the CR157, weight is lower, yields are comparatively better. So again, we can say the battery activity versus CR600 series confirmed. Selectivity is also slightly improved. So today we have 80 plus catalyst references worldwide in non-Axens design CCR, including repeated orders. So 35 plus competitor design units in operation with the Axens catalyst. All competitor CCR design type, atmospheric, pressurized, cycle max generation with and without closeout, replacing all catalyst density types. So today we have almost 200 references in 9 years, so which shows the success story of next generation Symphony catalyst. Thank you.
Thank you, Mr. Ravinder Kumar. You started by mentioning about the typical problems in reforming catalyst, surface area loss, stability issues, and then went on to show how they are all improved. And the targets of any refiner, higher octane, higher liquid yield, higher hydrogen yield, long life, and also at lower cost. The higher hydrogen yield will have a specific more importance in the future when green hydrogen comes in, because this is outside the purview of the mandates that will be coming. Thank you very much for your insights.